Every day you see headlines, right? This new drug works. This new diet is better than the old one. But how do we really know if the difference they found is legit, or if it's just a fluke? Well, that's exactly what we're going to dig into today. We're going to look at how data tells the real story.
So here's the big question. When you see a study and it shows, a new treatment helped a few more people than a placebo, how confident can you be? Is that a real effect? If they did the whole experiment over again, would they get the same result? These are seriously high-stakes questions, and luckily, statistics gives us a way to find the answer.
So how do we do that? Well, the main tool for the job is something called a confidence interval. It's this brilliant idea that helps us get past just looking at simple averages and instead helps us understand the uncertainty that's, it's always lurking in our data.
Okay, I know, that sounds super technical, but the actual idea behind it is pretty straightforward. See, when we look at two groups, we can easily calculate the difference between their averages. But that's just an estimate from our little study. The confidence interval gives us a much better picture, a plausible range for what the true difference is out there in the real world.
Yeah, let's put it this way. Instead of just saying, the new drug improved things by exactly 8%, a confidence interval lets us be more honest. It lets us say, look, we're pretty sure the new drug improved things by somewhere between 5% and 11%. And that range, that's everything. It admits our data isn't perfect, and it gives us a much more realistic picture of what's going on.
All right, to really see how this works, let's dive into a case study. This is from a real study that used sheep, actually. And researchers wanted to answer a huge question. Could embryonic stem cells, or ESCs, actually help a heart heal after a heart attack?
Okay, so take a look at the results. Each of these dots shows the change in a sheep's heart function. If it's a positive number, that means improvement. On the left, you've got the group that got the stem cells. On the right, the control group that got nothing. Just at a glance, your gut tells you the group on the left is doing better, right? But our gut isn't enough. We need the numbers to be sure. So let's look at those numbers. We had 9 sheep in each group, a pretty small sample. But look at that third column, the one with the X bar. That's the average change. The stem cell group improved by an average of 3.5%. Meanwhile, the control group, their heart function actually got worse, dropping by about 4.3%. Whoa, that seems like a really big difference.
Now, before we get too excited and start calculating, statisticians have this little checklist they have to run through, just to make sure the math is going to be legit. First, were the groups independent? Yep, the sheep were assigned randomly, so we're good there. Second, is the data all wonky with crazy outliers? Nope, it looks pretty normal. Okay, we are cleared for calculation.
So, what's the simple, straightforward difference between these two groups? Well, we just subtract one average from the other, and we get what's called a point estimate, a 7.83% improvement. But, and this is a huge but, that's just one number from this one experiment. It's our starting point, not the finish line. And this is where the magic happens. We plug our numbers into the confidence interval formula, which takes into account stuff like the sample size and how spread out the data is, and we get this, a range. This is our 95% confidence interval. It tells us that the true benefit of these stem cells probably isn't exactly 7.83%, but it's very likely somewhere between a 3.32% and a 12.34% improvement. And this is how we can make a really strong, confident conclusion. We can say, we are 95% confident that this treatment actually works. And here's the most important part. Look at that range. The entire thing is positive. The lowest plausible value is still an improvement of 3.32%. That means 0 is not in the range. So we have really strong evidence that there's a real positive effect here.
Okay, so that first case was pretty clear-cut, but what happens when the data is a little murkier? Let's switch gears and look at our next case study. This one looked at a sample of newborns in North Carolina to see if there was a link between a mother smoking and her baby's birth weight. And here are the charts. On the left, babies whose mothers smoked. On the right, babies whose mothers didn't. And you can kind of see it, right? Maybe a slight shift to the left for the smoking group, which would suggest lower birth weights. But it is nowhere near as obvious as that heart study, is it? It's much messier.
So it's probably not a huge shock that when the researchers crunched the numbers, this was their formal conclusion. They found insufficient evidence of a difference. Now, hold on a minute. Given everything we know today about the dangers of smoking, that seems wrong, right? It's a surprising result that should make us stop and ask why.
So this is the big puzzle.
If we have tons of other research showing that smoking during pregnancy is harmful, how could this particular study fail to find any evidence of it? In statistics, our starting point is always the assumption that there's no effect. That's called the null hypothesis. And this study couldn't find enough evidence to say that was wrong. And that failure is actually a fantastic learning opportunity.
When you get a result like this, there are really only two possibilities. One possibility is that, hey, maybe in this specific group there really wasn't a difference. But the other, and frankly the more likely explanation, is something called a type 2 error. This is a huge idea in stats. It's when an effect is really there in the real world, but your specific study just wasn't powerful enough to find it. You missed it.
So what's the usual suspect when this happens? What's the #1 cause of a type 2 error? Well, 9 times out of 10, it's because the sample size was too small. If the real difference is subtle, you need a lot of data to be able to detect it. Think of it like this. You're trying to see a tiny little germ with a cheap low-power microscope. The germ is there, but your tool just isn't strong enough to let you see it. This study's sample was probably just too small.
Now here's where this gets really interesting and frankly a little chilling. This is a real quote from the chairman of the tobacco company Philip Morris back in 1971 on national television. He's taking the fact that babies born to smokers are smaller and he's twisting it, trying to spin it as a good thing. It's just a shocking reminder that understanding this stuff isn't just for a class, it's a critical shield against misinformation. So let's pull all this together. After seeing these two very different stories, one clear, one muddy, what are the big lessons? What can we take away and actually apply when we're looking at data that compares two groups?
It really boils down to this super useful 4-step framework. First, prepare. What's the context? What's the real question here? Second, check. Is the data any good? Did they do it right? Third, calculate. Okay, let's crunch the numbers. And fourth, and this is the most important one, conclude. What does it all actually mean, and what are the limitations?
Look, if you remember nothing else, remember these 3 things. 1, a confidence interval, that range, is way more valuable than a single number. 2, this is the big one from the smoking study. No evidence of an effect is not the same as evidence of no effect. It might just mean your microscope wasn't powerful enough. And 3, sample size, sample size, sample size. It's so often the key to whether you can trust the results.
And that kind of leaves us with one final thought. Now that you know all this, the next time you see a headline about some new study, you're ready. You can think a little more critically. Maybe the first question you ask isn't just, so, which group won? But instead, how big was their sample, and what did that confidence interval really show?